Okay, hello everybody. Thanks a lot for the introduction. I'm Frederick. I'm a PhD candidate at TU Delft, working with Christian Siemes. And my PhD is basically on the transplant modeling. So in this presentation, I will go a bit more into the effect of the aerodynamics on that. So as you are all aware and is already pointed out, it's clearly an issue has arisen both for GRACE and GRACE follow-on, which resulted in one accelerometer not being operational or have an increased noise level. What is the solution to that? A transplant, which is basically a replacing signal for this accelerometer. Our methodology focuses on doing it through non-gravitational force models. So if we have the blue satellite here, basically we take the acceleration from the accelerometer through our high fidelity models that we have. We go to density and wind. This density and wind we then transplant to the other satellites based on the argument of latitude. When we then have the density and the wind, we apply again all models, so radiation pressure, and we calculate again the full acceleration. Which is resulting here. In this presentation, no thruster firings are modeled. So to go to an aerodynamic model, to go to density and wind, we of course need an aerodynamic model. For this, we have three options, from left to right with increasing complexity. So you can have a constant drag coefficient, which can only model drag. So in the relative wind velocity, the panel model, which can also predict lift, which makes it a bit more accurate. And then finally, you can do DSMC simulations where you basically throw a bunch of particles onto the satellite and you see what the average force is. And this can not only take into account drag and lift, but also multiple reflections and shadowing of the satellite by itself. Now we want to compare the quality of the transplant. So this is done through these plots. What you see here is on the horizontal axis the time, and on the vertical axis the argument of latitude. You see four different plots. So the three bottom ones are the different models, so constant drag coefficient, panel model, and DSMC model. The top one is a very simple one where we basically just do an attitude correction to the accelerometer data of the working satellite, and then move this to the malfunctioning satellite with also a time correction or a position correction. And what we can see here is that we have these diagonal features which are linked to the attitude of the satellite. But most importantly is that when you use a constant drag coefficient, it's actually performing worse than just doing an attitude correction. This is really a motivation to go to more advanced models. Now, people have done things like adding an artificial pitch angle, which is indeed increasing the accuracy again. But we, however, prefer to go to a panel model or a DSMC model. These two you can see are very similar. There is some variation, but the magnitude is for sure lower. And it's also quite constant over the orbit. So there is probably still some bias, which we can correct.
1 minute left.
Yeah. Then I go to my last slide. What you see here is the power spectral density. The blue one is the signal, and then you have the orange and the green one, which are here, which are actually already, let's say, 100 times below the actual signal, which is the attitude and the position deviation only and the constant drag coefficient. But then if we go to a panel and DSMC, it's about a factor of 10 times better, which is of course very important. It's mainly better at the low frequencies. At the high frequencies, the noise level is then taking over, but it is typically at these low frequencies that we need to have for the time variable signal to retrieve. So conclusion, the aerodynamic model matters. Constant drag coefficient performs worst. You can't use tricks, but okay. But if you use a panel and DSMC model, they perform very well and almost equally well due to the convex shape of the satellite. So thank you very much. This was a very quick presentation. If you have questions, feel free to ask, or you can always reach me. Thank you.
Thank you, Frederick. Good to see some work on the ACC.
Yes.
Transplant, yeah. We'll keep going. Next up is Matthias Freyer, and he will talk about analysis and investigations post-fit residuals.
Yes, am I audible?
Yes.
Very nice. And you can see me as well, I believe. Good. Yeah, I'm trying to talk very quickly about the investigation of post-fit residuals of GRACE and GRACE follow-on. Yeah, as we heard earlier this day, we have plenty of measurements, more than 20 years of GRACE, KBR gravity fields and their respective residuals. We have approximately 4 years of good or more or less good quality LRI data and also combined data gravity fields. And here we have, in our center, we also produce gravity field coefficient as well as post-fit and pre-fit residuals. On the right side, you can see some standard deviations taken from my colleague, which should just show that our gravity field solutions are very competitive among the analysis centers. We have also made some recent changes in the processing strategy, which is not part of the presentation today. But it mainly focuses on noise modeling, which had improved our solutions even further. Speaking about post-fit residuals, here we investigate the signal content of the residuals after gravity field estimation as well as before, which is illustrated here on these two plots. So on the left side, we have the pre-fit residuals. And when we estimate real harmonic coefficients and accelerometer parameters as well, we get the post-fit residuals. And on the right side, we see there is still some signal left in the residuals. And one of our tasks is to identify and analyze these signals. And here I have an exemplar of what can be seen. So here I've marked the shadow entries. They are well known and well prominent. Which is a little bit more difficult to see are the panel effects here in this visualization. And of course, we also have these LRI blindings. So a different approach utilized by my colleague UCAR Koch. He assigned the long time series of GRACE and GRACE follow-on K-band residuals to a grid cells among the Earth and estimated periodograms of each grid cells. From that, he extracted some dominant peaks and could assign them to known ocean tide constituents. Here, and this is what he had found. So in the residual signal, he found some constituents that are already were included as background model in the processing, but he also finds some frequencies that are not included in background modeling. Which is perhaps the foundation of future modeling approaches for ocean tides. And with this, I've also finished. So I was very quick. The conclusion is that the analysis of residuals shows systematic effects, just as I shown here, shadow, panel, and sensor characteristic like the LRI blindings. There are even more, which is not part of today. It helps to improve the overall understanding of the satellite platform. It helps to improve the understanding of the environment of the satellite. For example, thermal couplings are visible in the residuals. And from the analysis of my colleague, we can also estimate ocean tide errors at over 30 tidal frequencies. And we also found some major tides, gravitational excited tides of degree 3, nonlinear tides, and radiational tides. That's all from my side. In the extended version, you can see even more. And if you have questions, I'm really happy to answer them later in the session.
Thank you, Matthias. That was great. Thank you for staying well within your allotted time. On your last point here, tides, that's also the topic of our next talk, given by Christoph Dahle, ocean tide background modeling during GRACE gravity field determination.
Yes, so it's me again. Let me just share the screen. All right. So
yep, good to go. Looks good. Okay, go ahead.
Yeah, let's start if I can. Hopefully, click to the next slide. No, okay. So let's start with a little motivation background for this presentation. So ocean tide models are inevitable background models needed in level 2 gravity field processing. And currently we think, at least maybe other groups have the same impression, that there are a few drawbacks. So In general, there are various global ocean models available, but they are provided in different formats, and they have different tidal constituents contained. They provide usually tidal constituents for a number of major tides, but are missing minor tides. So admittance needs to be implemented into the software packages by the users. Some of the formulas and definitions regarding tides can become complicated or easy, not so easy to understand for non-experts. There are some phase definitions which make things complicated. So to summarize, each new OceanNet model requires, in principle, the adjustment of the source code. And because of that, a new unified approach is proposed. The goal is to have a user-friendly and model-independent framework. There's a dedicated web page here. Currently on that web page, 8 OceanTide models are available. Also one mixed OceanTide model consisting of tidal constituents composed by 3 different independent models. Also one atmospheric tide model is available. Each model is represented by 3 files. These 3 files describe the number of tidal constituents and minor tides that are interpolated, plus all the additional files for the with the Stokes coefficients, and they're provided in ACGM format. And there's also some reference code that can be used by users. Some results that we have investigated. So at GFC, we have implemented this new approach in our software and tested the impact of different OceanTide models based on our Release 7P solutions, which I already mentioned before. We made 2 investigations. First one is the systematic comparison, and the second one is how we decided which OceanTide model we used for Release 7. And the assessment criteria are first that we analyze KBR post for the residuals, and second we looked at the ocean RMS of the resulting gravity fields. So let's start with the first experiment. So this is a systematic assessment.
1 minute left, Christian.
Yeah, thanks. The key conclusions, which are based on one test here in this case, are that completely omitting minor tides is not a good idea. This is quite obvious, but here this variance reduction plot shows that quite impressively. What's interesting is that adding degree 3 tides, in this example here, we used the tides from time 22. First of all, slightly improves the global ocean RMS, but also clearly reduces the post residuals in dedicated regions. And we also can conclude that additionally adding more minor tides gives further reduced residuals in certain regions. And then the second test was the OceanTide model test for GFC Release 7. Here the main conclusions are that all new models tested perform better than the old FAST 2014 model that we used for GFC Release 6. We had the question before, what's the individual impact of the different improvements? So here the numbers in the legends are maybe a little small, but they tell us that simply using a more recent OceanTide model improves the ocean RMS by about 7%. And amongst these new models, we found out that FASS and GOD perform quite similar, but we see some advantages for GOD 5.6 in the Weddell Sea. The best model is actually the mixed model. And we also found out that the mixed model that is provided at this website I mentioned, if we slightly modify this model, then we obtain even better results. And this modified model is then the final model that we also have used or are using for GFC Release 7. And I think I will end here. And I encourage you to really look at the uploaded slides. There are much more figures and results presented there. Thanks.
Thank you, Christoph. Great overview. Keep going with the next talk from Markus on more details processing strategies for the upcoming GFZ Release 7.
Yeah, thank you, Felix. So this is the presentation about the GFZ Grace Classifier follow-on Level 2 data release 7. So yeah, motivation is simple. So current GFZ release 6 Grace follow-on standards have not been changed for more than 6 years. So it's time for reprocessing for release 7 time series, which aim at reduced noise time level of gravity field solutions, reduce tempo, aliasing errors, and more realistic formal error estimates. And in order to reach these goals, we apply an improved stochastic modeling of observations, as we have heard before, also from the other setters, CSR, JPL, and background model errors, meaning that we use an BCM matrix for aliasing model. And we perform an arcwise iterative variance component estimation for an optimal weighting between the two observation components, high-low and low-low SST. And this table gives a short overview about major changes in terms of instrument data. So we will use for both missions the reprocessed version 05 level 1B products from JPL. However, these are not yet fully available. So in the release 7P solutions, this data is not yet included. Further, we will reprocess the GPS constellation to be conformed with ITRF 2020, IGS 20. And this is currently being processed. So therefore, it is also not yet included in the results presented here. And then in terms of background models for the static field, we will switch from the Eigen 64 field to XGM 2019. AOD model will be switched from 6 to release 7. The ocean tide model, as we have heard before, we will change from FAS 2014 to this mixed model. And atmospheric tides will be the new time temperature model. Yeah, the main results here we can see for the time period for Grace 2003 until 2014. On the left, we can see degree amplitudes in terms of unfiltered residuals relative to a cost-G climatology. In black, release 6, in blue, release 7P. And on the right, RMS variability relative, again, to cost-G climatology with Gaussian smoothing applied. And what we can learn from these plots are clearly visible. Improvements of release 7P versus release 6, reduced noise from degree in order 15 onwards, especially over the oceanic regions, and also more realistic formal errors. And yeah, this is the ocean RMS plot, as we have seen before with Christoph. Again, residuals relative to cost-G climatology with Gaussian smoothing applied. So in average, we have a drop of ocean RMS values from 5.5 to 3.7 about for release 7. Standard deviation is also going down from 2.6 to 1.6 about, and then the improvement in terms of percentage values is about a little bit more than 30%, with minimum and maximum values between 10 and a little bit more than 50%. Yeah, with this, I'm coming to conclusions and outlook. So our level 2 products will include a reduced noise level, more realistic formal errors compared to release 6. The new components are the stochastic modeling of instrument errors, stochastic modeling of AO background model errors, and the optimal weighting of the low-low and high-low SST component by means of variance component estimation. And last but not least, we plan also to release LRI-based fields for Grace follow-on, and publication of release 7 is planned then for the end of this year. beginning with the GRACE mission. And yes, more information can be found in the large slide package. Thanks.
Thank you, Marcus. Thank you for staying within time. We'll keep going with Martin Lassap from the Astronomical Institute at the University of Bern. And Martin will talk about the status and outlook of time variable gravity field determination at EUP. Martin,
yeah, can you see the screen?
Okay. Yes.
And here, at least see the screen, not necessarily me.
Yes.
Okay, perfect. So I will quickly try to sum up what we have been doing at our institute with GRACE follow-on data. If I can jump here. So our gravity field recovery is probably based as most other institutions on a little detour, which means we take GPS observations to GRACE follow-on and estimate in-house kinematic positions, which we then take together with the KBR and LRI observations to estimate reduced dynamic orbit and the gravity field. So what we do is based on the celestial mechanics approach. Basically, all is done in-house. We use our own GNSS constellations. We estimate PCV maps from residuals, and we apply integer fixed ambiguities. So for the parameterization, we use daily arcs. We estimate initial conditions, bias in 3 directions. For the ACC, we estimate scaling factors and off-diagonal elements for a full scale matrix, all in daily arcs. And in addition, we estimate, that makes perhaps characteristic for our approach, we have a lot of nuisance parameters, so to say, which we call pseudostochastic parameters, which are constrained piecewise constant accelerations in minutes in radial on-track and cross-track directions to account for all kind of unknown deficiencies, so to say. So this is what we do per arc, plus we estimate the gravity field in monthly batches up to degree of order 96 as it's common. Now, there is, as for everybody, a ton of force models to be subtracted. And in our case, we have now updated the ones in red, which is the ocean tides. We tested a few of the new ocean tides models and came to the conclusion that the mixed ocean tide models are a mixture of the GOT56 model, which is great, the FES22 model, and the time model for certain tides works best. That is quite good model, slightly better than the GOT only, published by Theo Graz. Then we use atmospheric tides from the time model, plus we use the AOD release 7, plus also incorporated the error information of the AOD release 7, which is really helpful for us. And for the accelerometer data, we now have only used the ACH, so stemming from the ACX and ACX2 bundle. For our noise modeling, just very quickly, so we have these piecewise constant accelerations, which are constrained, and we use variance component estimation to estimate the magnitude of those constraints. And in addition, we apply a noise model from post-fit residuals, where we just have an initial solution and then compute post-fit residuals, a noise model based on serial correlation of the post-fit residuals. Now, the parameterization is now extended by additional, what we call pseudostochastic parameters, and now it's spherical harmonic coefficients, still at the daily level up to degree and order 96. And those are now constrained with the AO error information provided by Linus Schihor as a group of Henrik. For now, we do not, we stopped estimating a variance component for those because we found out that it's simply 1. So those numbers seem to be very well working within our approach.
1 minute.
Now, perfect. Let me just jump to the results. Huge jump here in what we do. So in terms of ocean RMS, this is all the models contributing to the COS-G operation combination for GRACE follow-on monthly gravity fields. And blue would be our old solution. Now let me just jump back and forth with all the changes I just told you. So the blue line is jumping down. We really see a significant improvement that really stems from including the error information of the AO and updating the ocean tide model and the AOD model to the newest solution. And nice for us, or nice in the cost-G combination, is that also the combination profits of that, of our solution being updated in that case. So hopefully everyone with release 7 will then drop with us as well. And just one very quick test I wanted to show you, because I think I haven't seen it. Probably it's well known. For 2024, I did some tried to test the temporal resolution. So what can we achieve actually from 5 to 60 days accumulations of gravity field solutions, based on a previous selection of modeling, and just in a simple RMS over the ocean plot. And I found that one can, so this is for each month, so obviously it's better the longer we average, but one can fit this quite well with a very trivial power fit, just to see what we can achieve. And our 30-day resolution is definitely not the last stop. So we can definitely go lower in the future when one has time. So that's it. Just a summary. We have updated the background models that really improves the solution noticeably. The AO error is very good and crucial. One should definitely use it. For us, it's very important to estimate proper variance components for our piecewise constant accelerations. Realistic variance information is given by proper observation noise modeling. Well, ACX2 for the white pointing months are very important. And what is the next step for us is hopefully to really finally update our course screening procedure. So thanks for your attention, and I'm happy to answer questions.
Thank you, Martin. Yeah, we'll collect the questions and have that in the discussion session. We're going to keep going and with the presentations. Unfortunately, we need to skip over the next one again. That was going to be from Brian Dennis' team at Goddard, spline mass-cons for enhanced mass change recovery. Hopefully, he'll be able to provide that and link it through the agenda when they're back. Instead, we're going to jump over and continue with Jean-Michel Lemoyne, and he's going to talk about the L3 and L4 products out of CPAESS and the release 5. Jean-Michel, go ahead.
Can you see me and hear me?
We can hear you and see your slides.
Okay, that's okay,
Yeah.
I guess. This presentation provides an overview of CPAESS Level 3 and Level 4 products and the changes we plan to implement in our next graceful data reprocessing. I would like to acknowledge my co-authors, particularly Alexandre Bouganemi. Oh, sorry, I made a mistake. Alexandre Bouganemi, Eric Pellereau, and Julia Pfeffer from Magellan, who are now responsible for the operational production of CPAESS solutions from level 2 to level 4. Since we had to significantly shorten our presentation, I have a single slide dedicated to our level 3 products with an example. This example is a manometric product, that is to say, the geographically correlated mass trend in the ocean obtained from an ensemble of solutions. On the two top rows, you have the manometric trends from 6 real analyses. The first observation is that the spread between the reanalysis is large. And the second observation that you will see on the bottom row, you have here the ensemble from the reanalysis. In the middle, you have the ensemble from the mass counts. And here you have the ensemble from the spherical harmonic solutions. And you see that while the two GRACE solutions coincide more or less, they are fairly different from the ocean reanalysis ensemble. So, and in particular, in the North Atlantic Ocean, there is a great difference between the reanalysis and the GRACE solutions. And these signals are the main source of non-closure of the sea-level budget. These products can be downloaded from this site, and you will have more details from Alexandre Bouganemi's presentation in 12 minutes. So I switch now to the improvements that we want to implement in our new release. The first one is on the tides. You have here a view of the polar view of the Earth. On the left, you see the ocean tides from FAESS 2014. These are the errors computed from GRACE thanks to the accelerometric residuals. And you see that in the entrance of the Hudson Bay, FAESS 2022 has been much improved, and also a much smaller scale improvement here in the area of the Vancouver Island, where on the left, FAESS 2014, on the right, 2022. And you see that the red dots have disappeared in the new release, thanks to a much finer representation of the bathymetry in this area of the entrance of the canal and also of Seattle. Second improvement, we plan to
1
switch.
minute left.
Thanks a lot. Switch to the new computed de-aliasing products from Toulouse or from the Observatoire de Toulouse, namely using the ERA5 ECMWF 3D atmospheric potential computed by Pascal Gégou, and the new Tugo barotropic model from Florent Liard, based on the fine mesh of FAESS 2022. For that, I have here, it's a bit long to explain, so I will probably skip, but the fact that all these indices here are below the 0 line indicate that the new models perform at least slightly better than release 6. These are 2 months of determination.
Thank you, Jean-Michel. We'll keep going and save questions for later. Next up is Mikhail, I hope I pronounced that correctly, or not too badly, at least, from Delft, on purely data-driven sub-weekly mass change models from GRACE residuals.
Yep. Thank you very much, Felix. So my name is Miguel or Michael, that's perfectly fine. I'm from TU Delft. I'm a PhD candidate under João Teixeira Encarnação. And the topic is indeed of my PhD, purely data-driven sub-weekly mass change models from GRACE residuals. So the idea is, how can we construct GRACE-only sub-weekly mass change models using purely post-fit range rate data, and then also have, for the data user, estimated associated uncertainties. So the presentation outlook quickly in this lightning round, note the actual framework itself, some results, and preliminary uncertainty estimations. The framework itself is quite a big chunk. The idea is really to relate these post-fit range observations, these KBR observations, directly via an empirical method, directly to equivalent water heights for our data users in hydrology. And the idea is to separate this into 3 blocks. We first look into how we can pre-process these post-fit residuals into line-of-sight gravity differences, into ranged residuals, and grid them spatially and temporally. Combine these to obtain these 5-day grids of these observables. The second block tackles the idea of how to transform from these along orbit observables to equivalent water heights. And this basically goes into this empirical model that you can see here in the slides. It's a very simple quadratic model, a quadratic term, a scaling term, and a bias. The observable itself, we are taking it as a weighted average between the line-of-sight gravity differences and the range observables, because this combines both the frequency content that localizes nicely mass anomalies from LGDs, but also gives us a bit of a wider range to cancel out the lobes that these LGDs contain. The empirical framework for the uncertainty estimation is quite straightforward and very important for data users. It is composed of 3 parts. The observable uncertainty itself, this is from instrument error analytical spectra models. The interpolation error, as we are spatially interpolating, that of course generates an error. There is a regression. We are performing a regression, so of course there is a regression uncertainty parameter from it. related to the design matrix from the regression. And lastly, as I think it's quite an important thing for data users in hydrology and other fields, and an uncertainty of the level 2 products themselves should be quite important. And in this case, we are using a ensemble mean, ensemble distribution of all the data centers. So what does this result in? We are now looking into a comparison between ITSG daily solutions resampled at 5-day mean and our 5-day solutions from TU Delft. And you can see that there is quite evident hydrological sub-weekly signal from active river basins such as the Ganges-Brahmaputra, as it's described here. Also, we have quite higher frequency content as we are reaching up to degree 57 compared to 40 for ITSG. And purely based on, thank you, and purely based on regression, the noise from the instruments, we have an uncertainty below 2 centimeters, which is quite a good thing. Importantly, we don't only have land hydrology, we also have quite interesting co-seismic sub-monthly signals, something that quite is important. And we can actually observe during the Tohoku, for example, within the month of March, the actual co-seismic signal that Grace can feel, and the same thing for the Sumatra in 2004. So yeah, that's about it. Again, if you have any questions, please feel free. The whole point is to indeed relate well these LGDs, these along orbit tracks, into equivalent water heights directly via this empirical model. Thank you very much.
Thank you. Very interesting. Again, please collect your questions for later. I'll put them in the chat. I already see there's a bit of a discussion going on some of these presentations, so we can use that format as well and revisit that when we get through the presentations in this session. Next up, we have Khosrow Gobadi-Farr from CU Boulder. Khosrow is going to talk about monthly mean time variable gravity inversion from GRACE for laser ranging measurements using the LGD approach.
Hello, everyone. Can you all see my screen and hear my voice?
Yes, loud and clear, looks good.
Perfect, thank you. So my talk is about monthly L2 solutions from GRACE follow-on laser data using the LGD approach, and this work is a collaboration between me and my PhD students, Evan and Vityars. So the reason that we decided to produce our own L2 solution from GRACE follow-on laser is that Vityars needs the post-feed LRI residuals for validation of the error of the static gravity models, and the KBR L2 solutions do not fit the LRI data at frequencies above 60 CPR. And this is expected because if you look at the PST of KBR, you will see that it starts to increase at 60 CPR, but that of LRI decreases to 200 CPR. So we use the LGD approach to compute the spherical harmonic coefficients of gravity up to degree 180 from 1 month of data. So this figure here shows the degree RMS of the KBR-L2 solution from JPL in blue and the degree RMS of LRI-L2 solution from CU Boulder in red. So as you can see, there is good agreement between the two up to degree 96, which is the maximum degree of the KBR solution. These two spatial maps here show the surface mass change in terms of equivalent water height from the KBR solution and from our LRI solution, using the coefficients up to degree 45 and no filtering applied. So if you look at our the surface mass change that we get from our LRI map, you see that a small scale mass changes, for example, over Patagonia and Caspian Sea, have a similar quality to those in the JPL solution, which gives us confidence, some confidence in our solution. And the same conclusion can be drawn if you apply a de-striping filter plus a Gaussian filter to these L2 solutions. So the LRI L2 solutions contain a small scale gravity signals beyond degree 100. To demonstrate that, here I show the pre-feed and post-feed LGD LRI residuals bandpass filtered between 100 and 180 CPR. So that's what you see here. So this result clearly demonstrates that our LRI L2 solutions are capturing the small scale gravity changes beyond degree 100. And this is also true about the small scale gravity changes associated with the smaller scale mass changes in West Antarctica, as you see. So when you go to the post-phase, the signals disappear, which means that the L2 solution, because this is post-phase, right? It means the L2 solution is capturing that. So I wanted to end my talk by just talking about these high degree coefficients. So we all know that these high degree coefficients are dominated by temporal aliasing error, right? But I think there's still some real geophysical signal that we can accurately extract from these high degree coefficients. So to demonstrate that, here I compute elastic deformation in Antarctica using the LRI coefficients from degree 60 to 100. So I start from degree 60, basically this frequency band which is dominated by temporal aliasing. So if you look at the West Antarctica in the vertical elastic deformation, you see some signal which may or may not be real deformation. The east-west elastic deformation purely shows the noise stripes, right? But we all know that GRACE provides the most accurate gravity information in the north-south direction. So if you look at the north-south elastic deformation in West Antarctica, you see this pattern, which seems to be real geophysical signal, real deformation signal. So when you add or remove a mass change, it causes north-south deformation with opposite signs in the north and south of that mass anomaly, which is exactly what we are seeing here. And as you can see, they are perpendicular to the GRACE.
1 minute left.
Sure. And they are perpendicular to the GRACE stop, which is another sign that this is real geophysical signal. So we next in our plan is to validate this using some GPS data. But the point that I wanted to make in this slide is that we should not simply dismiss the coefficients, these higher degree coefficients in LRI solution, because we think they are dominated by temporal aliasing error. Because temporal aliasing error, as you see in the three maps, is not manifested similarly in different geophysical signals that we compute from L2 solutions. So for the take-home message for my talk is that there is value in releasing the LRI L2 solutions for GRACE C to a much higher degree than 60, because some geophysical quantities such as the north-south vertical elastic deformation may benefit from those higher degree coefficients, although they may seem to be totally dominated by the temporal aliasing error where you look at the degree RMS. And the maximum degree of LRI L2 should be greater than 150, and therefore I believe it might be a good idea to release the LRI data for GRACE C with a 1 second sampling rate, which is basically what we had for GoCheck radiometry data. Thank you for your attention.
Thank you, Khosrow. Some interesting ideas there that we can maybe revisit in the Q&A session. Sorry, I'm trying to find my agenda here. Here we are. Next up, we have a presentation from Alexandre Bouganime on developing advanced gravity products and services at CNES through the SAGSA SAXA project.
Yeah. Can you hear me, everyone?
Yes, we can.
Yeah, thank you very much. So, hi, I'm Alexandre, working at Magellium, and as Jean-Michel presented earlier, we are now in charge of producing the gravity solutions for CNES through level 2 to level 4. So if you go to the next slide, please, I will show you the context for this project. So since the launch of GRACE and then after GRACE FO, the CNES has been producing two types of L2 solutions and one L3 ensemble. So first, an unconstrained solution. You can see an example on the right-hand side that has been contributing to the COSG project. And also a second solution that has been stabilized through SLR data using a truncated singular value decomposition. That is the standard solution for the CNES, provided both at monthly and 10 days time intervals. And both of these L2 solutions can be found on the links you can find on the presentation. I invite you to download it. And also the L3 ensemble has been distributed since 2019 and now will be distributed easier through the SAXA project. So if you go next slide, I present to you the main the state of the CNES solutions. So as of today, we are now up to date with every available data from GRACE and GRACE FO and produce solutions that are comparable, that remain comparable to other production centers. And so next slide, I will now present you the main scope of the SAXA project. which aims to provide a data and service center for the gravimetry for CNES, led by Magellium, and to ensure the production and distribution of all gravity products. So that includes level 2 solutions and also level 3 ensembles, and as well a level 4 application product in oceanography, climate sciences, hydrology, and cryosphere monitoring as well. And as of now, we are estimating that by late 2025 and early 2026, the data center will be fully operational for almost all level of production, and that by mid 2026 to late 2026, all level 4 products will also be distributed on the Geode CNES platform. So as of today, almost all products are already available in the several platforms such as HydroWebNext or Aviso. I invite you again to download and grab the links. And the aim is to centralize most of the production. So if you go on the next slide, I will show you a few examples of the applications. I will try to be brief. So some products we are already distributing are, for example, barystatic sea level estimations available on the website Aviso, which have been the focus on several publications, such as Barnou et al. 2021-2023 and Bouy et al. 2025. But also ocean heat content and Earth energy balance estimates also available on Aviso and the subject of several publications. On the next slide, I show you other applications. So this time, not on ocean ocean study subjects, but more on the cryosphere on the right and hydrology on the left. So for example, if I start by hydrology product, several projects use the CNES gravity products.
1 minute left.
Yeah, I will quickly sum it up. So we produce some added value products such as river flow. So you have an example on that, which is the focus of a publication that is submitted and awaiting the returns. But also we participate in partnership with the Legos and the CNES to more global projects such as IMBI and GLAMBI, and we aim to participate as well on the follow-up of GLAMBIs this year. So on the next slide, on the final slide, I'll sum up everything. I have put for you the different links to the distribution, the data portal for the distribution. Please note that some of these pages are under construction and will not be operational right away, but we expect them to be fully operational by the end of 2025. And on the next two slides, I've put for you some bibliography and the relevant data portals that will be useful for everyone. And I invite you to follow up this project and follow up our production. And thank you, everyone.
Thank you very much, Alexandra. Very exciting work. We have 4 talks left in this morning's session. And after that, we'll have a bit of time to follow up with questions to individual talks. Next up is Evan Wilson from the University of Colorado. Evan's going to talk about long-term polar motion trends and their impact on GRACE follow-on pole tide corrections.
You on mute? Yeah. Can everyone hear me?
Yes, we can.
Great. Hi, everyone. My name is Evan Wilson, and I'm a second-year PhD student at the Department of Aerospace Engineering Sciences at the University of Colorado Boulder. I'm studying under Koster Gabati Farr and Steve Neeram, and today I'll be talking about the long-term polar motion and its impact on the GRACE follow-on pole tide correction. So polar motion is the nutation of the Earth about its axis of rotation, and it predominantly consists of 2 periods, the 14th-month Chandler wobble and the 12-month annual wobble, which you can see in the full time series plot in Figure 1. There's also long-term and interdecadal variability that is driven by mass redistribution in and on the surface of the Earth, as well as a long-term linear trend from GIA. And you can see that in this Figure 2 here, that the long-term GIA-driven polar motion is the dominant contributor to pre-1995 data, and then around 1995, the polar motion diverges, which is due to present-day ice mass loss. So to apply the pole tide correction per the Warr et al. 2015
recommended pole tide correction, the GIA-driven linear trend must be removed since the C21, S21 values from GIA models, which are commonly subtracted from GRACE data, contain their own GIA pole tide correction. It is our understanding that the CSR and JPL centers use the old IERS time series, which was changed around 2018, and they updated the pre-1972 astrometry solutions. The data shown here is the different IERS C01 products with 3.40 year with Gaussian smoothing, and then the linear trend values calculated from the 1900 to 2000 period, which removes the present day ice mass loss, which we don't want to have contaminating our GIA linear trend. We can see that the change in pre-1972 C01 data significantly impacts the long-term trend that we get for the GIA pole tide. And you can see that the old C01 IERS EOP trend is nearly 300% for the XP and 130% for the YP. And just to go over this plot really quick, the current data is shown in red and blue, and the old in green and black. So using the trend computed from the previous IERS EOP series and a commonly used GIA model, I6GD, there will be a potentially significant residual degree 2 order 1 signal. And you can see in blue, the old IERS rates are plotted, and then the orange is the I6GD polar motion. The current IERS data shown by the red triangle agrees better with I6GD as well as new GIA models such as the Bellis-Manley GIA model, and the rates are plotted there in black. But more work needs to be done to understand the reliability of the polar motion time series as well as understanding how the polar motion is calculated by GIA models. So conclusions. The new GIA linear trend derived from current IERS C01 products is significantly different than the previous trend, which will alter the GRACE follow-on pole tide correction. And to be consistent with current IERS data, the pole tide correction should be updated with the new linear trend from the current IERS C01 product. The current IERS EOP derived trend will agree better with GIA models, which will help to remove the GIA pole tide and reduce any degree 2 order 1 residual signals that are non-physical and are from the pole tide. But more work needs to be done to investigate the IERS data as well as the polar motion reported by GIA models. Thank you. And if you have any questions, please feel free to email me. Thank you very much.
Thank you, Evan. That looks very interesting. I'm going to have some follow-up questions when we get to that. We'll keep going. Next up is Krzysztof Sosnicka from the Institute of Geodesy, University of Wrocław in Poland. He's going to talk about the missing relativistic oblateness orbit correction in the IERS conventions and the impact on GRACE follow-on products and MAGIC orbits.
Thank you. Can you see my screen?
Yes, we can, and we can see you and hear you well. Yeah.
Yeah. Okay, thank you. So my talk will be about the orbital corrections related to general relativity that are currently included in the IERS conventions. So currently we have 3 corrections that are included: the Schwarzschild, lens sphering, and geodetic precessure, or the Sitter effect. But they all assume that the Earth is a sphere. We know that this is not the case. So we tried to test what is the impact of neglecting the real shape of the Earth or the next approximation of the Earth shape on different satellite orbits, including spherical satellites like LARES and Starlet used in satellite laser ranging to derive low-degree gravity fields, as well as GRACE follow-on, and the second pair of MAGIC satellites, which will be the inclined with the inclination of about 70 degrees. Here we have the formula for the acceleration caused by the oblateness, relativistic oblateness, relativistic C20 effect. For the classical acceleration, we would have just this term, so nabla times R, where R is the potential related perturbic function caused by C20 or J2. And for the general relativity, we have in fact 3 components that have to be taken into account, and everything is divided by C squared. So in principle, the acceleration, the resulting acceleration should be small. We need to work out the nabla R term, which is given here, and also this component. And after putting everything into this equation, we end up with the final acceleration. Let's have a look at the order of magnitude of the accelerations we expect. So the largest accelerations are, of course, caused by the main term, the Schwarzschild term, but Schwarzschild causes more or less a constant acceleration in the radial direction and does not cause any accelerations in the cross-track direction. Here we have lens-fearing de Sitter, which is also called the geodetic precession, and relativistic C20, and the scales for these 3 components are the same, so they are all 10 to the minus 10 meters per second squared. So we see that the relativistic C20 acceleration is more or less of the same order as the Sitter. The Sitter is included in the conventions. Relativistic C20 is not included, even if we have larger accelerations in the radial and along track components. Here we have a comparison for Gray's follow-on, MAGIC, and higher orbiting LARES-1 and Starret satellites. So for the near-polar orbits like Gray's follow-on with the inclination close to 90 degrees, the cross-track accelerations are close to 0. Whereas if we go to the lower inclination angle, we will have some periodic accelerations in the cross-track component. Now let's have a look at the results. So we run a test using real Gray's follow-on data, one solution without considering this correction and the second with considering this correction. The scale is here from minus 1.5 millimeters up to 1.5 millimeter. So we see a clear systematic pattern. So this is not just a noise, the effect that is buried somewhere in the noise of the solution, but we see a clear oblateness-like pattern in the Gray's-like solution. And if we look into the spherical harmonic domain, of course, the largest impact is on the C20. But we have also some impact on the correlated coefficients like C40, and the impact on C20 is 3 times 10 to the minus 12, which is comparable to the level of the formal errors of currently derived C20 values using SLR data. So the relativistic C20 effect is larger than the geodetic precession that is included in the IRS conventions, but the C20 relativistic effect is not included. The accelerations are at the level of 10 to the minus 10 meters per second squared and cause systematic patterns at the level of 1 millimeter in terms of the geoid height and the products based on Gray's follow-on. Thank you for your attention.
Thank you. Appreciate your talk and presentation. We have 2 more talks in this session, both on mean gravity fields. First one is going to be given by Chaoyang Zhang from CSR on an updated intermediate mean gravity field, GIF 63.
Okay, give me a second to just swap the presentation. Okay.
Yep, no worries.
Oh.
Looks
Okay.
good now.
Okay. Yeah, thank you. So today I'm going to talk about our new updated mean gravity field model, GIF 63. So as many of you probably have known that we have kind of like anomaly at this band of GGM-05C, roughly 90 to 150. If we project that into spatial domain, you can see those anomaly, continent-wide anomaly in those places. And we find some correlation with the EGMOA data coverage as you see those white gray area where we don't actually have data in EGMOA. So we feel like GGM-05C is kind of probably over-constrained towards EGMOA. So we reprocessed the latest GRACE data and the GHOST data, and we do more careful covariance calibration before we combine those two data set. As you can see, the GRACE mostly contributed below degree 150, while GOCHE is above degree 150. And so how does that look like right now? As you can see, so on the top, it's the same plot for GGM-05C at this band. Well, at the bottom is new combined GRACE and the GHOST mean, and we get rid of all those anomalies. But as you can see from the triangular plot at a very high degree, especially above 220, the GRACE GHOST combined mean is still need some surface data to stabilize them. And also the closed zonal above degree 180, where we have the GOCHE polar gap, also need some surface data. So we brought up the XGM-19 to stabilize the very high degree. But we also need to make sure for the GOCHE band, roughly above degree 180 and below 240, we don't want to we want to still keep its contribution into the new GIF63 model. So as you can see at the top, the GGM-05C, we see that continental anomaly again at this GOCHE band, but in our new model, we just keep the GOCHE contribution, but also get rid of those patterns in our new model. So next two slides going to be about our evaluation. On the right, we use the KBR post-fit variance to test all three model. 2-year data used. So if the model is better, we should have a smaller post-fit variance. As you can see, the continental anomaly in GGM-05C, but at the XGM-19 and the GIF63, we both get rid of those patterns. If we take a closer look at those two models over Greenland, you see the GIF63 actually is slightly better as we do the difference between the two models, and the GIF63 is smaller. And the second test, we also use the GRACE follow-on laser data. As you can see, both GIF63 and the XGM-19 is quite clean as compared to the GGM-05C. We just want to notice one tiny difference between GIF63 and XGM-19 over West Antarctic, where GIF63 is actually smaller. Well, yeah, that's pretty much all for this very short 4-minute. And then if you'd like to learn more, you can just hop into the full presentation online. Thank you.
Thank you very much, Xiaoyan. Very interesting. Okay, last but not least in this session this morning, Vidyarth, I hope I'm pronouncing that okay, Kumar, from the University of Boulder. We're going to talk about validating the uncertainty estimates of global static gravity field models using GRACE follow-on LRI data.
Hello everyone, I am Vidya Thirumulai Santana Kumar, PhD student at the Department of Aerospace Engineering Sciences at University of Colorado Boulder, working with Professor Khosrow Gobadifa. Today I'll be presenting my research on the topic validating the uncertainty estimates of global static gravity field models using GRACE follow-on LRI measurements. So each static gravity field model comes with its own associated errors, which is used for reporting the uncertainty of gravimetric quantities like geoid heights, and also used in global gravity field modeling. This work presents a novel framework to validate the errors provided by the static gravity field model using the GRACE follow-on LRI measurements by the LGD approach proposed by Gobadifar et al. In 2018. The methodology for this work basically follows like we have the model errors and we are kind of validating that with the help of observations. The observations in our case is the pre-fit LGD LRA residuals with respect to a static gravity field model. So when I remove the time variable gravity solutions, which is the LRA-L2 solutions developed at University of Colorado Boulder by Costro, I'm left with the post-fit LGD LRA residuals, which contains the error in the static gravity field models along with the errors in time variable gravity solutions and the sensor noise. Then I determine the PSD from this, which is the PSD of post-fit residuals. For the models, so each model has its own errors, which is kind of denoted as sigma CNM and sigma SNM. With that, we assemble the noise covariance matrix, which is CXX. And we propagate this noise covariance matrix to LGD. We call this as the data covariance matrix. And from the data covariance matrix, through discrete cosine transformation, we determine the PSD, which we call the PSD model. And finally, we compare both of these in the spectral domain. For the results, we have the noise floor as the post-fit residuals computed with respect to GOCO 2025S. And the first model I'm discussing here is GGM05C static gravity field model. The blue line plot shows the pre-fit LGD LRA residuals, and the green line plot shows the post-fit residuals. And the red line plot shows the LGD determined using the error provided by the GGM05C static gravity field model. In this model, we could see the basic idea is that if the PSDs match, if the red plot and the green plot matches, then the error provided by the model is reliable. With that idea, we could see that beyond 20 millihertz or 111 CPR, the error provided by this model agrees with the post-fit residuals provided by the GGM5C post-fit residuals from the LRA measurements. When I go to Eigen 5C model, we could see that the error pattern provided by the model kind of perfectly aligns with the post-fit LRA residuals, and beyond 17 millihertz or 96 CPR, we could see that the error provided by the model perfectly matches with the error provided with the post-fit LGD LRA residuals. When I go to ITG Gray's 2010S model, beyond 10 millihertz frequency, we could see that the fit is perfect in a case that the post-fit LGD LRA residuals matches exactly with the error provided by this model. So this kind of validates our approach, which we use to validate the error provided by the static gravity field model. And the final model I'm discussing over here is GOCO06S. Earlier, I had said that we have a noise floor of with respect to GOCO 2025S model, which means that if the error uncertainty estimates provided by by any model if it is less than the noise floor, then we can't use this approach to validate the specific model. So this is a classic example for that, because the post-fit LRA residuals is not accurate enough to validate the uncertainty estimates provided by the GOCO06S model. So this is one of the limitations, which means that if the error provided by the model is below the noise floor, then we can't use this approach to validate it. And also we can't use this specific approach to validate the errors below 8 millihertz of frequency band, because below 8 millihertz, it is dominated by the time variable gravity signals. So as a take-home message over here, we have provided a novel approach to validate the error provided by static gravity field model using the LRA measurements, which we get from Gray's follow-on, using the LGD approach proposed by Gobadifar et al. In 2018. Moving forward, we are planning on extending this analysis to use an entire noise covariance matrix rather than just using the errors to get the variance components of the covariance matrix. And that's it for today. And if you have any questions, please reach out to me. Thank you so much.
Thank you. Thank you, Vidyas. Great presentation. All right. This marks the end of the second session this morning. Let me just double check so I'm not missing anyone here. We do have 2 poster presentations that don't have a live component, but they're in the agenda. You can view them there and follow up with the authors if you have questions. So in a regular meeting, we would now head to coffee and we'd have some FaceTime. If you're in a position, if you're willing, if you're able, I invite you to turn on your cameras. We can maybe see each other, have some actual FaceTime through this virtual format. I do want to give a shout out to all the presentations and presenters. Thank you for sticking to that format. I know it's a lot to go through and to digest. Yeah, here, so I see people popping in. Good to see some actual faces to those names. I want to give a shout out, if there's a silver lining, if anything, to this format is that many people can join remotely. I see some Grace royalty here, Chris Reitber, Byron Tapley, Mike Watkins, Bernard Funon. Great to see you all in the meeting. Srinivas, Byron, I think I already mentioned that. Great to see you all here. So now it's time to follow up with some questions. If you like, this is really your time in the community to dig a little deeper. We have about 20 minutes left. Go ahead, raise your hand if you have a question. If I don't see a hand, we can go through the chat. I had asked the question early on to Marcos. He had answered that about the processing of the LRI data at GFZ, if that follows the same parameterization. Marcus, do you just want to speak to that real quick? I know you answered in the chat, but maybe you can.
Yeah, in principle, so it will be the same processing strategy except for the BCM matrix, and yeah, except for that, everything will be the same, I think.
Okay.
Yeah. So yeah.
Do we have raised hands? We do have a couple of raised hands. Let's go there first. David, go ahead.
Yeah, I have a question for Michael from Delft on the submonthly gravity fields using the LGD. I thought that was really interesting. I was wondering if you could comment a little bit on how you chose the quadratic model, and then I'm really curious about if you could comment on kind of the uniqueness of that estimation. Like, you know, are there other collections of equivalent water height signals on the ground that could also explain the LGD residuals at the submonthly timescales? Have you thought about those things, and can you talk about that a little bit?
Yeah, thank you for the question. I mean, the idea of the quadratic model comes from the pure fact that I'm not compensating for altitude effects, which is a very important thing, because as the gray satellites, the orbits decay, they of course go down, and then the anomaly of course is felt differently. So that's where the quadratic term tries to compensate for these effects, but also for along orbit effects, a little bit other effects that are not mass anomalies. So that's where the quadratic term comes into play, and it actually is a bit of a minor term. It's not the dominant term in the relationship between KBR observable, whether it's LGD or this combined observable. The main term comes purely from the scaling, because at the end of the day, if we simply look at the spatial patterns of LGD observables and KBR observables, there's a big correlation between them and the mass anomalies. They really localize these mass anomalies. So that's where the idea of this relationship comes from. And I'm sorry, the second part of the question, could you yeah. Sorry.
I wanted to ask about the uniqueness when you do. I guess it's the scaling is your dominant effect, is what you're saying. So when you aggregate, you know, when you're doing an estimation on the grid, are there other collections that you could think about shifting mass spatially that could also, you know, explain those residuals? Have you thought about the uniqueness of that inversion?
Yeah, exactly. So the whole point is that there is no inversion. It's purely a regression. I mean, there is an inversion in the fact that you're regressing, but there is going to be. So there are in the uniqueness of it is that there are some issues to the as typically they are, but some issues with the methodology, specifically near the Amazon. There is quite some deviations west and east to it, which I am nearly sure that we hypothesize here at UDEL that it's purely related to the fact that, well, it's not an inversion, so it's directly assuming that the mass anomaly is under the satellites, which of course it isn't, even though these anomalies are not very large, because these are compensated by the fact that we are using two different frequency domains. So we are using the LGD that really nicely localizes a mass anomaly, but then we are using the range that has much more of a, if you want to say it, a more thicker component, and that nicely compensates these effects. And actually, in this hybrid formulation, we we try to compensate as much as possible. And the uniqueness of it, yeah, I mean, it's been inspired, I think, from a little bit of papers that have been commonly now using these LGDs, these along orbits tracks to directly see instantaneity of equivalent water heights. I think that's something that was quite interesting with this method, is that you could use these spatially distributed these spatially distributed parameters, and just simply put your along orbit LGDs or ranges, and you could then have an instantaneous estimate of equivalent water heights, which could be also something quite nice. I hope that somehow answers your question.
Yeah, no, it's very helpful. Thank you. Appreciate it.
Thank you. We'll go to, there's two more questions, raised hands. Matthias first, and then Evan. Matthias, go ahead.
Yes, thanks everyone for the presentations. I have a question concerning the last presentation from Vidyard. So the PSD looked very interesting for me. I was wondering which kind of filter you used in order to produce these PSDs also to the LGD data.
Could you hear me?
Yes.
Yeah. So I just used the Welch periodogram for the observation part, and as I said earlier, for the models, I'm using the discrete cosine transformation, and for periodogram, we just go with the normal filter, the rectangular window. That's it.
Okay.
Okay.
Thank you.
Thanks. Evan, go ahead.
I have a question for Felix. So in the release 6 of the Grace follow-on, do you know if you use the old IRS C01 EOP product for the pole tide correction or the current one? And follow up to that, if that's so, are you going to update in release 7 the pole tide linear trend using the new IRS C01 product?
Yeah, I'm going to bounce that question right over to David or Chris. We were actually texting in the background trying to figure out what we're using to. So, David, you're mute.
Yeah, I think we're going to get back to you. We have a live text thread right now.
Yeah.
We're going to hold that.
Okay, great. Thank you.
But I had a related question. And maybe I need to go to the more detailed presentation. Is the thing that the using one or the other pole tide correction is then incompatible with existing GIA models, or the GIA model that we use to correct the data with also needs to be compatible with a certain pole tide model, or is that not the case? I was unclear about that.
I mean, the second thing is true. So in the War et al. 2015 paper, War really covers that pretty well, but the assumption is that the GIA model perfectly recreates the GIA-driven pole tide, and then the trend that we subtract from the full IRA or the EOP time series, whatever you use, has to perfectly also capture the trend in the EOP of GIA. And so kind of what we discovered and why we need to go more into detail about this is that different GIA models predict different rates of the polar motion that don't necessarily agree with the IRS time series. But it seems like with the current IRS time series, it agrees better with like I6GD, for example, and then Ashley Bellis-Manley's model, new model that will be coming out, also agrees pretty well too. And that it's that disagreement that really generates kind of this artificial degree 2 order 1 signal. But you can't like uniquely say which one that's coming from, because if there's a difference, it'll show up. I hope that answers that.
It does. I'm going to have to dig a little deeper. The context I'm asking in is always also motivated by the fact that when we estimate geocenter through the current TN13 approach, we have removed the GIA model from the data, so that whatever the residual trend is then goes into the TN13 product. So if you change the GIA model and of course the pole tide model in the data itself, that's going to not only impact CS21 but also geocenter potentially, right? So, and all that then trickles down into things like the global sea level budget. So anything large scale has the potential here to move the needle a little bit So it's always something to be aware of. And it's also something to be aware of when people substitute TN13 into their solution and do some mix and matching that can have an impact. And sometimes that's compatible, sometimes it's not. It's just something to be aware of. So I'd like to follow up with you and Ashley, and there's others here on the call that look into this kind of stuff, so we can properly, at a minimum, quantify uncertainties and the impact on geophysical interpretation of the data. Do we have more sort of live questions? Jakob, go ahead.
Thank you. Maybe coming back to tides with a comment. So Christoph Dahle, for example, was talking about difficulties to do ocean tides correctly. The more we are working on ocean tides and the better the GRACE results are becoming, I would put it slightly different. We are seeing things concerning ocean tides because satellite gravimetry with this GRACE principle is so sensitive to tides. So of course we are seeing things. So probably there is maybe no other observation system that is as sensitive to ocean tides than satellite gravimetry. And therefore, I think it's time to think this a bit differently. So the challenge is, of course, about how to extract this from satellite gravimetry together with altimetry and the other data sources we have. So it's less. Well, of course, it's difficult, but to put the emphasis on how much information on ocean tides we have in this system.
Okay. Does anyone want?
That's not really a question, but except if Christoph would have a comment on this.
No, I don't really have a comment on this comment, but what I presented first of all was this new unified approach, how to handle ocean tides in orbit and gravity field determination. And I think this is independent from what you just said, Jakob. So this still, I believe, is or makes it easier for all of the groups doing orbit and gravity field determination to handle ocean tides. And then we can probably dive into all the details and see what satellite gravimetry sees, but don't have to deal with all the other difficulties or inconsistencies regarding ocean tide models.
I had one sort of comment, obviously the SDS centers, JPL, CSR, GFZ, Goddard 2, we've been evaluating ocean tide models. If you've seen the presentations, we are updating them. With regard to evaluating the model, there's certain metrics you can look at, right? Like a reduction in global RMS, improving post-fits. Of course, the tides are most dominant in terms of amplitude right up on continental shelves. And if you look at these large-scale metrics, we might improve it a little bit over a very large scale in the interior of the ocean. But I'm always wondering if we're doing the right evaluation in terms of improvements where it matters at the land-ocean interface, in particular near Antarctica and the ice sheets, and how that interacts with trend estimates or with data combinations with other data types. So if anyone has thoughts about wanting to look into tide model improvements in those areas where you are impacted by aliasing on the land side or the ice side or under ice shelf side, I'm wondering if there are some things we should be doing that we aren't doing or that we can do better. Anyone have any thoughts along those lines?
Can I say I cannot find my reaction with the hand up? Oh, I found it. Sorry.
There you go.
Yeah, there we go. So I do think that in Antarctica, especially, we look at the Weddell Sea, we need to mask the tide there if you want to look at the ice on land. And I don't know, there are like some updated bathymetry. I'm wondering how using those bathymetry would help, to improve. I think that's worth doing. There are like some updated product under the ice shelf, and maybe using those, would help too. Because we always mask, put mask on when we solve on the ice shelf to avoid to have leakage from there, because we find that there is the calm on the ice sheet if we don't.
Okay. Tyler, I see you have your hand up.
Yeah, I'm not super surprised to see improvements around Antarctica. It's one of the worst places that we have tides. And going from FES to GOT 5.6, the new GOT models use cryosat-2 data over the ice shelf, so we get improvements there just by the empirical model. Whereas I believe the FES models are just hydrodynamic, which is going to be more sensitive to the uncertainties in subshelf bathymetry. And yeah, you hit the nail on the head that the aliasing errors we've always known have been a problem in the subshelf. I think there was a talk at a Grace Science Team meeting in, I don't know, a decade ago from I think it was Killet and David, I think you were part of that too. But yeah, so I'm not surprised. I think it's awesome to see the improvements that we can do with the new tide models. I think that we're only going to get better when we have SWOT data and Grace Funnel 1 and Grace C having both missions up. It's going to be great for tides.
Okay, thanks for that perspective. Okay, we have kind of 3 minutes left on the clock. I think I do want to end the meeting so promptly at 1:30. So do we have any remaining questions, comments? I think everything in the chat has been kind of answered live. If we missed something, we can always follow up later. If there's no question, really, I'm happy to give you a couple minutes back, or your morning, or your evening. So,
Chris, could I make one comment? I haven't been able to find my hand yet over here. I'm still a novice with this Zoom session going on here.
No worries.
It's really, really great session this morning, and I'm very impressive with the presentation that everyone gave going forward on it. This tide issue going out of it is an interesting question going forward, but the one point over here, Grace is not the best device for going at it. The best information comes out of the altimetry missions over here, and the interesting thing you're talking about, how we actually build in that seashore problem or nearshore problem going out of it. That's altimeter, or maybe the laser altimeter added to the radiometric altimeter may give us the best ways to go into it. But the first models, improvements from space, came out of these earlier altimeter data. And it seems to me that that's the best place for trying to improve the models going out of it. The problem with the aliasing between the tidal coefficients and the gravity coefficients makes that really a difficult parameter recovery mode. But in any event, that's one of the thoughts that I would have going forward on it. One of the thoughts we're wrestling with this issue in-house at CSR here. But in any event, I'll turn it back over to you just as a comment there.
No, I appreciate that comment, Byron. It's great to see you here. Okay, so yeah, that wraps up our first day of the science team meeting. I think we are making the best out of this situation where we have to just shorten everything. I really want to thank all the speakers again for presenting your ideas in such a short time frame. If you have any feedback for the next 2 days, just send that to me, and we'll try to incorporate that. I hope to see all of you again for the next 2 days as you can dial in. It's really great to have that turnout. So we'll continue that with the session tomorrow morning, where we will kick it off with future missions, update on Grace C, NGGM, and other technology developments. So Thank you for dialing in. Hope to see you again the same time, same venue here tomorrow morning. And yeah, until then, and enjoy the rest of your day and the rest of your evening. Take care.